Well, thank you very much for this introduction. And before diving into carbon dioxide reservoirs of habitable exoplanet Waterworlds, let me introduce you what a Waterworld is. And an exoplanet Waterworld will be a planet that has accreted a significant fraction of volatiles, more specifically water, without retaining a large hydrogen and helium atmosphere. So on the slide, you have examples of two interior structures of exoplanet Waterworld. On the left here, there's a laser pointer? No? Oh, okay. So here you have an example of a water world that will be young or close to its star, and all of the volatiles will vaporize in a envelope above a silicate and iron core. And most of the current literature actually focus on habitable water worlds, where the water is condensed as high-pressure water ice, and possibly this water world, those habitable water worlds possess a global liquid water ocean in contact with a thinner atmosphere. So there are several ways to form water worlds. The habitable water worlds could form beyond the snow line of their stars. They could accumulate a comet-like amount of volatiles and then migrate inward inside of the habitable zone of the star. And a later accumulation of water by impact between planetary embryos is also possible. And both of those mechanisms has been played out as a robust prediction of numerical simulation of water world formation. A third mechanism would be a sub-Neptune planet that would migrate closer to a star, close enough that its envelope will be evaporating. So this star would be an M-dwarf, a young M-dwarf. M-dwarf will be a star that is cooler than the sun and redder than the sun, and also, during the young stages of M-dwarf, they are very active, and this activity would allow just an evaporation of this hydrogen and helium envelope, leaving more heavy volatiles at the surface of the planet. So actually, low-density planets in the Waterworld size range has been detected in abundance by ground-based and space survey. So here you have a radius and mass diagram with all of the crosses are a sample of exoplanets that has been detected. And here, as a guide of the eye, you have a line that represents a mass and a radius of the planet that will be 100% of iron. Here you will be a planet that will have an iron to silicate, an Earth-like iron to silicate ratio. And here will be a planet that will have an Earth-like core with equivalent amount of water on top of it. So solar system planets are here represented by diamonds. You have the Earth, Venus, and Uranus and Neptune that are here. And you see that there is a potential sample of planets here that could have a significant fraction of water in their interior structures. So there has been a statistical analysis of this exoplanet population that has been performed in the past years. However, their results do not provide a smoking gun for water world detection. And here you have 7 potential water world targets that have been detected a couple of years ago. Those are TRAPPIST-1 planetary system that possess potentially 5 water-rich water worlds that will be observed probably by the next surveys. So then back to the carbon dioxide reservoirs. Following the mechanism of formation of water worlds, they could have comet-like carbon dioxide-rich composition, because usually they form from a material that is far from the host star and beyond the snow line. So this figure here is just to show the possible range of CO2 to water ratio inside of the comets, and to show that this range is wide. And most of the current literature focuses on relatively carbon dioxide-poor water worlds. So the question here is, if we actually accrete a comet-like amount of CO2, which could be a lot, where the CO2 would go inside of the habitable water world, and what could be then the main carbon dioxide reservoir of those planets. So what we did is that we developed an interior structure interior structure model for what we call sparkling water world, CO2 plus water world. And we try to incorporate the latest experimental results in our model. So I go very fast. I won't go into the detail in the complicated pressure and temperature, like phase diagram of water plus CO2 system. I just say that to account for all of the phases that could be present here, we use a Trend 3.0 equation of state that is a state-of-the-art industrial equation of state for water plus CO2 mixtures. And one of the first application of our model is to estimate how much of CO2 can be stored inside of the water-rich layers of those water worlds. So there is roughly two possible internal structures for habitable water world. So this is a cold version of a water world that will have a shallow ocean, a thick layer of clathrates being a crystalline structure of water, where water form cages that can entrap molecules, here CO2, and then high pressure ice. And a hotter version of a habitable water world would not have this clathrate layer. And we limit our exploration temperature to 400 K because this has been shown as a limit, the highest temperature for life as we know it. So the CO2 can be dissolved in the ocean, can be stored in clathrates. And for this first results, we consider the high pressure ice is actually pure water ice. So this is an example of interior structure that we get with our model. Here for the cold version, you have the pressure and the composition of CO2 inside of the profile. The scales here are different. So for the colder version, the shallow ocean actually store a few percent of CO2, while the thick clathrate layer can store up to 15% of CO2 inside of it. For the hottest version, there is a discrepancy between what model predicts and what actually all of the current models' equation of state of water plus CO2 would predict, and the very recent experimental data. So here in white, the equation of state would predict a decrease in solubility of CO2 in water for at saturation for pressures above 100 MPa, while the experimental data show that this solubility increases and reach up to 20% here at 3 GPa of pressure. So what we do is that we compute those profiles, we sum the total amounts of CO2 that we get from those profiles, and then we divide by the total amount of volatiles in the hydrosphere of the planet. Total amount of volatiles meaning water plus CO2. And then we compare it to the possible range of cometary compositions. Here this range is shown in gray. And this figure shows that, first of all, the hot water worlds are the one that store the most of CO2 inside of them. So yeah, sorry, the y-axis here is the total planet volatile fraction, meaning that here, for example, it's a planet that accreted 50% of volatile by mass. So yeah, I was saying that the hot water worlds are the one that are able to store the highest amount of CO2 because of this increased solubility of CO2 with depth, and this red line takes account from it. And the second result that is shown in this figure is that a planet that has accreted more than 11% of volatiles by mass are unable to reach this comet-like composition. Meaning that if, for example, those planets actually accreted a comet-like composition of CO2, so a very rich composition of CO2, this excess has to go somewhere. And one of the obvious possibilities for the CO2 is just to go in the atmosphere, right? To have a very thick atmosphere of CO2. However, in that case, the water world would not be habitable. So the radiative transfer simulation show that if we have more than 100 bar of CO2 inside of the atmosphere of a water world, the temperature will rise above this 400 K limit, and then the water world would not be nice for life as we know it. So here we propose that the carbon dioxide could be stored as CO2 ice or as a newly discovered carbonic acid monohydrate solid, because both of the CO2 ice here and this solid have their densities that are higher than the densities of high pressure ice, meaning that they will be stably stratified, stably stored under those layer of high pressure ice and away from the atmosphere. And this is what we want to preserve the habitability of water worlds. So the question is how to get those solids there, and we are working on it. And this is kind of a big picture situation to show you one of the possible mechanism of what is happening to store the carbon dioxide inside of this water world. And we think that actually the habitability of the water world might be determined during the cooling history of the planet. So here you have an example of a water world that is accreting, that has a supercritical water plus CO2 envelope, uniformly mixed, very hot. And depending on the condition of the cooling of the water world, if those conditions are favorable for CO2 to actually rise and stay in the atmosphere, then those water worlds are possibly non-habitable because we will creating those CO2-rich atmosphere with very strong greenhouse effects. However, if the conditions are favorable for the CO2 to sink and to form those ices or the solid, then the CO2 will be trapped, and this outcome will be possibly habitable. Okay, so here's my summary. So the atmosphere, the ocean, and the clatrate layer are actually of water worlds are not enough to store a comet-like amounts of CO2 if the water world accreted more than 11% of volatile by mass. If we want to avoid a hot and non-habitable scenario, we need to sequester CO2 away from the atmosphere inside of the high-pressure ice mantle. And the habitability of the water world would probably depend on the cooling history of the planet and the extent of the carbon dioxide solids are stored inside of this high-pressure water ice layer. Yes, thank you. I'll be happy to have any questions.
For questions, maybe come to the mic if you wouldn't mind, because I think they're streaming. Thank you.
Hi, great talk.
Thank you.
I was wondering if your model considers speciation of carbon dioxide as things like bicarbonate and carbonate.
That's a really good question. So the model is pure water and CO2, right? So if there is no other agents such as calcium or like water-rock interaction, coming from water-rock interaction, the speciation will be minimal. So.
Even with pH? Because it can't buffer and change the pH of the system.
So yeah, but to lower the pH, you need additional to put the pH higher. You need additional agents to do that, and the model does not account for them. So that would be actually a great addition. But I think we will hear about salts inside of the water world later. Yeah.
Cool. Yeah. Steve Vance, JPL. Really nice work. Glad to see you're using the results from Abramson et al.
Yeah.
I had a question about the structure. Getting a 2,000 kilometer thick high pressure ice layer. There was the issue of the thermal profile in such a thick layer.
Mm-hmm.
I would just expect for a large world you have a lot of radiogenic heat from the interior, and it would be hard to have an ice layer that thick that was isothermal rather than following close to the liquidus of the high pressure
Mm-hmm.
ice. So just wondering what you did to model the temperature structure of the ice.
So yeah, the parameters of the model has been kind of optimized to have a maximum storage of CO2. So what this slide doesn't tell is that the isothermal profile is only inside of the ocean and clatrate layer, not inside of the high-pressure water ice. The high-pressure water ice has an adiabatic profile, actually.
Okay. Even in the ocean, compressibility of the water will lead to a drastic temperature increase by the time you get to the high-pressure ice.
Yeah, I agree, but it also will lead, like the increasing temperatures will decrease the solubility of CO2.
Yeah.
So keeping those isothermal profile getting really the upper level of the maximum of CO2 that you can possibly ever
Okay,
ever
you're setting
store
an
there.
upper bound.
Yeah,
Okay.
exactly.
Okay.
It's an upper boundary.
Good. Well, just one quick question.
Go ahead.
Is the high pressure ice in this on the left starting at 10 megapascal or 1 megapascal?
I think it's starting around 600 MPa.
Okay. Okay.
Yeah.
Just clarifying. Good. Thanks.
Hi, Owen Lemur, and I was just wondering if your model has a sync term for cations coming up from the silicate interaction with the high pressure ice, or if that's something that could be put in.
So no, my model does not account for that yet.
Okay.
Yeah, thanks.
Cool. Thank you so much. So